Welcome to U7L2 Intro to Probability. So probability measures the chance or likelihood that a specific event will occur. Okay? One important part of probability is the sample space. So the sample space is a set of all possible outcomes. For example, the sample space for a scenario about flipping a coin would be heads and tails. Okay? So the sample space, is all possible outcomes. The fundamental counting principle can be used to find the total number of outcomes for an event that involves more than one scenario. So it can have 2 scenarios, 3 scenarios, 4 scenarios, and basically you just multiply everything together. Okay, now this only works for finding the total number of outcomes. Okay, the total number of outcomes. It won't tell you what the outcomes are, but it will tell you how many there could be. So if one scenario can occur in m ways, for example, and another can occur in n ways, then both of those activities can occur in m times n ways. Okay? So for example, if you have to flip a coin more than once, and every time you have 2 options, then you would just multiply 2 times 2 times 2 as many times as you would end up flipping the coin. Okay, that's an example of what that fundamental counting principle does. All right, example 1, create a tree diagram for each of the following scenarios and identify the sample space and number of outcomes. So we're going to do a tree diagram, and it's going to be for the scenario rolling a standard die, then flipping a coin. So when you roll a standard die, okay, and if you don't know this, hopefully you'll learn about this in class, it has 6 sides, right? The numbers 1 through 6 are going to be on the sides. So when you roll it, you have 6 choices. You can roll a 1, a 2, a 3, a 4, a 5, or a 6, okay? So the first event happening is rolling that die, and those outcomes are the numbers 1 through 6. Then you're going to flip a coin. So for each number, right, you can either flip a heads or a tails. So under 1, I can flip a heads or a tails. I'll put H for heads, T for tails. Under a 2, I could flip a heads or a tails. Same thing for 3, heads or tails. All the way down, heads or tails, heads or tails, heads or tails. So when it comes to the sample space for this scenario, right, it's all possible results that could occur when you roll a standard die and then flip a coin. Okay, so the first option is going to be rolling a 1 and getting a heads. Another option is rolling a 1 and getting a tails. Another option is rolling a 2 and getting a heads. Then rolling a 2 and getting a tails. And you just keep doing that all the way down to get every possible option for your sample space. Okay, so let's write these out. So I'll put S for sample space. So that set is equal to, put my curly brackets, 1 and then a heads, or 1 and then a tails. 2 and heads, or 2 and tails. 3 and heads, or 3 and tails. 4 heads, 4 tails. 5 heads, 5 tails, or 6 and then heads, or 6 and then tails. So those are all of the options. If we count up the number of outcomes, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there's 12, which hopefully makes sense because of the fundamental counting principle. We had 6 options here, and then we had 2 options here for each one. Okay, and 6 times 2 gives us 12. Okay, so whether we count them up in the sample space or we use that fundamental counting principle from above, we're going to get that there's 12 outcomes possible. All right, keep it going. So without drawing a tree diagram, I want you to determine the number of outcomes for the following scenarios. So flipping a coin, then choosing a letter from the word math. So flipping a coin only has 2 possibilities, heads or tails. So there's 2 options there. Okay, 2 options there. Then choosing a letter from the word math, well, there's 4 letters, right? 1, 2, 3, 4. So there's 4 options there. So the total number of outcomes here is 2 times 4, which is going to give us 8 possible outcomes. Let's do the same thing again. Choosing a day of the week. Well, there's 7 days in a week. And then a number 1 through 9. The numbers 1 through 9 are 9 of them, right? So there would be 7 times 9 possible outcomes if we were to do this. And 7 times 9 is 63. Let's look at another one. Flipping a coin, then choosing a letter in the alphabet. Well, flipping a coin, there's still only 2 options, heads or tails. And choosing a letter in the alphabet, well, there's 26 letters in the alphabet. So now we have 2 options times the 26 from choosing a letter, and that's going to give us 52 total outcomes that could happen. 52 total outcomes. Part D, rolling a standard die 3 times. So we're rolling a die, and there's 6 options there, but we're doing that a total of 3 times. So we're doing 6 options, and then another 6 options, and then another 6 options. So we're actually multiplying 6 3 times, okay? So multiplying 6 3 times. I'm going to do this on my calculator to make it faster. 6 times 6 times 6. And we get 216. So there's 216 possible outcomes if you roll a die 3 times. So it's not 6 times 3, because you're rolling that die 3 times. It's 6 times another 6 times another 6. Everything you multiply has to be the outcomes for whatever the event is. In this case, it's rolling a die. E, creating a 4-digit passcode from the digits 0 to 9. So a 4-digit passcode. So there's 4 things. I'm going to lay it out that way. There's 4 things we have to look at. Okay, the first time we pick a digit for our passcode, it's from the number 0 to 9. And there are 10 numbers 0 to 9. So there's 10 options. But then I do that again. So there's 10 options again. And then there's 10 options again. And then there's 10 options again. Every time I choose a digit from 0 to 9, I have 10 options. Now we have to multiply all of those together. Okay, and if you multiply those all together, you get 10 followed by 3 zeros. So 10,000 options if you multiply those all together. 10,000 outcomes. All right, let's move on. On the next page, assuming all outcomes are equally likely, the probability of an event E happening is the ratio of the number of desired outcomes to the total number of outcomes. This is called theoretical probability. So assuming all outcomes are equally likely, which is an assumption we have to make when it comes to probability, the probability of an event E, so P parentheses E, is the desired outcomes, right? Like, say you want to know, okay, what's the likelihood I roll the number 1, right? Desired outcomes over the total number of outcomes for that situation or for that event. Okay? Now, probabilities can be between 2 numbers, 0 and 1. A probability of 0, although not super common, means that the event is impossible. Impossible. Okay. For example, if I say, okay, I have a 6-sided die, what's the probability of rolling a 7? It's impossible. There is no number 7 on that die. Okay. And then the highest that a probability can be is 1. Okay. 1. And that would be something that is certain to happen. Okay. So for example, if I say, okay, I'm going to roll a die, what is the probability that I get a number bigger than 0? That's certain, because all the numbers on the die are 1 or more. So they're obviously bigger than 0, right? So that's certain. But most probabilities lie somewhere in between 0 and 1, and they cannot be greater than 1. Now, they can be expressed as fractions, as decimals, or as percents. If they are expressed as percents, keep in mind it's 0% to 100%. Okay? Because 100% is equivalent to the number 1 in terms of what a percent means. 100% is the highest percent you can have, and it's equivalent to 1, okay? Okay, moving along. So now we're looking at example 3. The spinner below is spun once. Find each of the probabilities. So that spinner, let's just kind of take a look at it. Right now it's on 4, okay, but that's just to show it's a spinner, right? In general, there are the numbers 1 through 16, okay, all going all the way around. You can see they go in order, okay, and we're assuming that everything is equally likely. So we want to find a couple different probabilities. To find these probabilities, we have to figure out the desired outcome, right? How many outcomes are there in that desired outcome over the total possible outcomes? Well, the total is pretty easy to find here. It's the numbers 1 to 16, so there are 16 total. Okay, there's 16 total outcomes. All right? Now, the desired are going to change for each part of these of this problem, right, for A, B, and C. So P greater than 7, the probability that we get something greater than 7. So that's going to be 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 options. So there are 9 ways we can get something greater than 7. So there's 9 in the desired, and there's 16 total. Now, we would want to simplify this if possible. Here we can't. 9 and 16 don't have anything in common. So I'm just going to divide them. And then I get the decimal 0.5625. Now, you can either multiply by 100 or move your decimal 2 places to the right to turn it into a percent. And that's going to give us 56.25%. So, close to 50% likelihood that you're going to get something greater than 7. Next one, probability of a prime number. Okay, so you got to be really careful here. We're looking for prime numbers. So prime numbers are numbers that are only divisible by 1 in itself. And so that would be not including 1. 1 is not prime. 1 is not prime. So that would be 2, 3, not 4, 5, not 6, 7, not 8, not 9, because that's 3 times 3, not 10, 11 is prime, 13 is prime, and that's it. So there's 1, 2, 3, 4, 5, 6. Yeah, there are 6 numbers here that are prime out of 16 total. Again, the total hasn't changed. I can simplify that, dividing both by 2, so I get 3 over 8. If I divide 3 divided by 8, I get the decimal 0.375. And if I move my decimal 2 places to the right, I get 37.5%. That's the likelihood of getting a prime number. Then we can look at the last one, probability that we get a multiple of 3. So starting at 3, a multiple of 3. 3, 6, 9, 12, and 15. Just adding 3 each time, right? Multiples of 3. So 3, 6, 9, 12, 15. So there's 5 of them. So 5 out of 16, which does not simplify. So I'll just divide it. I get 0.3125. Okay, convert that to a decimal, or to a percent, excuse me. So that's going to be 31.25%. A little bit less likely than the prime number. All right, let's keep going. For example 4, Jared guessed on the last 3 true or false questions on his quiz. What is the probability he got exactly 2 of the questions correct? Okay, so if you're guessing on a question, there's only 2 options. You're either going to get it correct or you're going to get it incorrect, right? It's either right or it's wrong. So the question here is, what is the probability that he got exactly 2 of the questions correct? Exactly 2 of the questions correct. So every time he guesses, it's either correct or incorrect, right? And then we're trying to figure out what's the probability he gets exactly 2. So let's kind of look at the sample space for this by using a tree diagram, kind of like we did earlier in the notes, okay? So the first time he answers, okay, so his first answer, he either got a correct answer or an incorrect answer, okay? That's the choice. His second answer that he gives, again, it's either incorrect or correct. But now we have to go off of what we had before. So under correct, it's either correct or incorrect. And same thing under incorrect, right? And that's for the second answer he gives. Actually, let me color code this just to show you guys. Okay, so that's going to be the second answer he gives, okay? Now for the third answer he gives, his third answer, which is his final answer, because he guessed on the last 3. So his third answer in this scenario, again, it's either correct or incorrect. But now there's more choices from above that we need to continue from. Okay. So for every option above, he either got the next one correct or incorrect. So here's the idea here, right? Let's say that he got the first one correct, the second one correct, and the third one correct. That's one option, right? Or he could have got the first one correct, the second one incorrect, and then got the last one correct again, right? He could have maybe got the first one incorrect, the next one incorrect, and the last one incorrect, right? Maybe he got them all wrong. It could happen, right? But that's what this tree diagram shows us, all of the possibilities, putting those events together into one big event. Okay, so now in the sample space, we want to know what is the probability that he got exactly 2 right. So exactly 2 of the 3 are going to be correct. So what we're looking for is 2 C's. We're looking for any sample space that has 2 C's. So let's just write the whole sample space out and then figure out which ones have 2 correct answers. Okay, so our sample space here, I'll put it at the bottom. S is going to be equal to. I'm just going to start from left to right. So I'm just going to go left. I'm going to start here. And then I'm going to keep going to the right, basically changing as I go down. Okay, you'll see. So we're going to start with C, C, C. Okay, everything is correct. C, C, C. Then the next option is going to be, let me see. I'll change the color. C, C, but then I. Okay, so for that next one, you could have two correct and then an incorrect. So C, C, I. Next option, still starting at C, but going incorrect, then back to correct. So C, I, C. C, I, C. And then the last one over there is going to be C again, but I and then I. So C, I. Okay. And then we're going to have 4 more for if you got the question incorrect at first, right? Okay, so it's incorrect, correct, correct. So ICC. And then it's incorrect, correct, incorrect. So ICI. 2 more. Incorrect, and then incorrect again, and then correct. Okay. So IIC. Last but not least, we have incorrect, incorrect, incorrect. All 3 incorrect. So that's our whole sample space. Notice that there are 8 choices here. There are 8 choices here. 1, 2, 3, 4, 5, 6, 7, 8. Of those 8 choices, how many are exactly 2 correct? 2 C's. So let's circle them. So the first one's 3 C's. That's not 2. The second one's 2. The third one's got 2 C's. And then no for the fourth. The next one has 2 C's. And then we have only 1 C, 1 C, and no C's at all. So there's 3 options in the desired outcome. So there's 3 options in the desired outcome. Over, again, we already talked about it. The whole total was 8 outcomes. Okay, was 8 outcomes, which is how many we have in the sample space here. That's also what we get when we do 2 times another 2 times another 2, right? 2 times 2 times 2 is 8. So no matter what, we can see that total number of outcomes is 8. And we actually did this exact probability above, 3/8, and it equaled to 0.375. 0.375, which is equal to about 37.5% likelihood. So not super likely that he's going to get exactly 2 correct. All right, let's look at the next one. So example 5. Out of 60 students, 15 are taking calculus, 27 are taking physics, and 8 are taking both calculus and physics. If a student from the group is chosen at random, find each probability. And then we have 2 probabilities, takes calculus or physics, or takes calculus but not physics. Okay, so what we're going to do is look at this scenario visually. So we're going to do a Venn diagram. When we do our Venn diagram, we are going to create our Venn diagram with our 2 circles for calculus and physics, one for calculus, one for physics, and we're going to start in the intersection. We're going to start with what they have in common. Okay, so we're going to create a Venn diagram. So this box is for my universal set. Every number, right, the total, which is 60 students, because this is my total. This is my universal. Okay, that's my universal set. So in the box, there has to be 60 total. 60 total in the box. In the circles, everywhere, right? When I add all the numbers up, it has to be 60. Okay? I have to start with what they have in common. So we're going to draw 2 circles. Make sure they overlap. I'll label one with a C for calculus and one with a P for physics. And it says 8 are taking both calculus and physics. So I'm going to put 8 in the middle. So start with the intersection, which you'll remember from the last set of notes is what they have in common. So start with the intersection. Then work your way out. So now I'm going to look back at what it said at the beginning. It said there was 15 taking calculus. 15 taking calculus. Okay, cool. Well, if 15 are taking calculus and I already have 8 in the C circle, in the calculus circle, I already have the 8 accounted for, then I have to actually subtract that 8 from 15 to figure out what's left and what goes in this other section of that circle, right? Because the whole circle was C, the whole calculus circle can only have 15. So we're going to do, to figure out what goes there, we're going to do 15 minus 8, and that's going to leave us with 7 left to go in that other part of the circle. okay? We'll do the same thing with physics. So right now, we know that there's 27 total people taking physics, but we have 8 of them accounted for. So we're going to do 27 minus the 8, and that's going to leave us with 19. So there's 19 people taking physics who aren't in the calculus circle, right? Who aren't also taking calculus. Now we can figure out how many go outside the circles, right? Out here, by adding these numbers up and subtracting from our universal total of 60. So if we add up what we have so far, if we add up what we have, then we have 7. Here, let's do it like this. 19 plus 8 plus 7. If I add all of that up, 19 plus 8 plus 7, I get 34. Okay? If I add all those up. And then if I subtract that from 60, I get 26. So there's 26 that goes on the outside. There's 26 who aren't taking calculus or physics at all. Okay, they are students in the school or whatever the situation is, but they are not taking those classes, okay, that we're talking about right now. All right, so let's double check. You make sure all these numbers add to 60. So add these up, make sure they add to 60, so you can make sure you didn't make a mistake, okay? All right, probability takes calculus or physics. So that means anything in the C circle, anything in the P circle, just add those numbers up. So that's 7, 8, and 19. Well, we already added those up before, right? Right here. They got 34. So the probability that they take calculus or physics is going to be the 7 plus the 8 plus the 19 over the total, which is the 60 students, okay? So that's going to be 34 out of 60, which if we simplify that, we can divide by 2. We get 17 out of 30. So 34 out of 60, if you divide that, or 17 divided by 30, either way, you're going to get 0.5667 if we round, which is going to be about 56.67%. So more than half take calc or physics. Right? Now we're going to do the probability that takes calculus but not physics. So they take calculus, but they don't take physics, which means they can't be in the physics circle. So that crosses out the 8, the intersection, right? That's only the 7 here. So it's only the 7 who only take calculus. So 7 out of the 60 total. Can't simplify that, but I will divide it. And that's going to be about 0.1167 or about 11.67%. So there's not very many students, right, who take calculus but not physics, right? And so the probability of picking one of those students, if a student is chosen randomly, is not very likely. All right, perfect. Okay, let's move on. All right, a complement. A complement of an event is the probability of the event not occurring. So just like we talked about in lesson 1, complement meaning that it was something that was not in the set that we were talking about, right? It wasn't in the given set, but it was in the universal set. So it's the same idea with probability. It means that you want to talk about the probability that an event doesn't happen, right? So basically, the biggest probability that can ever exist is 1. So you start with 1. Well, let's write the notation out. Probability of the event, the complement of an event. So E with our little apostrophe. So the probability of the complement of an event happening. You start with 1, which is the biggest probability you can have, and you take away the probability that the event did happen. So probability of E. And that will tell you what the probability is that it is not going to occur. So for example, 6, the probability that it will rain tomorrow is 11 out of 15. What is the probability that it will not rain? So that's the complement. That is the opposite of it raining, is for it to not rain, correct? And so the probability that it is not going to rain, so I'll put P of not rain, is going to be 1 minus the probability that it does rain. Okay, so that's going to be 1 minus 11 out of 15. Okay, and that's going to be, so if we convert 1 into 15s, it'll be 15 over 15 minus 11 over 15. Run out of space here, which is 4 out of 15. Which is about equal to, hold on, let me move this over so I can actually fit all of this in here. Here we go. So 4 out of 15 cannot simplify. So I'll divide it instead. And what I got was 0.2667, which is about equal to 26.67% is the likelihood that it will not rain tomorrow, given that probability that it would rain at 11 out of 15. Okay. Last but not least in these notes, we want to talk about experimental probability. So theoretical probability is what we already talked about in these notes. Theoretical probability is saying, theoretically, based on the facts, the logic, how the numbers are working out, the total number of outcomes, the desired number of outcomes, here's what the probability will be. Now, experimental probability is based on results. It's based on results of repeated trials of an experiment, right? Such as rolling a die, such as flipping a coin, such as different combinations of a spinner, things like that, okay? It's calculated the same way as theoretical, except it's based on actual results, not expected results, right? It's not theoretical. It's actual numbers that happen when you did the experiment itself, whatever kind of activity experiment was happening, okay? So the spinner is spun 50 times and the results are shown in the table. So that's the experimental aspect of it. This spinner was spun 50 times and here's the results. Okay, it landed on red 5 times. It landed on orange 12 times, purple 7 times, yellow 16 times, and green 10 times. So these are experimental actual results here. Okay, and then it says find the theoretical and experimental probabilities if the spinner is spun again. So if that spinner is spun again, we're looking for the theoretical probabilities for each option that it gives us and the experimental probabilities of what actually already happened. Okay, all right, perfect. So taking a look at that, first of all, the totals are different for each situation. Okay, so if the spinner is spun 50 times, that's the total of experimental. Okay, that's the total of experimental because that's how many times that spinner was spun. That is what all of this data adds up to. Okay, all of that data adds up to 50. Okay, so that's the total for experimental. All right, now for theoretical, the total would be based on the spinner itself. So for theoretical, the total is going to be based on the spinner. So the total here is 5 because there's 5 colors, right? 1, 2, 3, 4, 5. So the total for the theoretical is 5. Okay, so the total here for theoretical is 5 and the total for experimental is 50. So that's going to change the number at the bottom of your probability, right? So for theoretical, it's all going to have a total of 5. And for experimental, it's all going to have a total of 50. I'm going to go ahead and write that right now. Now we just got to figure out that desired outcome. So that'll be the numerator. So the probability of getting an orange for theoretical, there's one orange on that whole spinner. There's 1. So the probability of getting an orange is 1 out of 5. And I'll just go straight to a percent. So 1 divided by 5 is 0.20. So that, or 0.2. So that's 20%. Okay, 20%. For experimental, however, the probability of orange is based on the results, which is 12 oranges. So that's 12 out of 50. I'll go ahead and divide it, get a percent. So 12 divided by 50 is 0.24 or 24%. Let's look at red or green. Red or green. So for theoretical, you have 1 red, 1 green. So that's 2 out of the 5. So that's 2 out of 5, which is equal to 0.4 or 40%. Whereas for red or green for experimental, we have 5 red, 10 green. Add those together, 5 red plus 10 green. You're going to get 15 out of 50. And that's going to be exactly 30% when you divide it. 0.3, 30%. Probability of not purple. So theoretical on the spinner, not purple is everything else. So here's purple, so not that. So that's 1, 2, 3, 4. 4 out of 5, which is equal to 0.8 or 80%. Whereas not purple on the actual results, so ignoring the 7, we have 12 plus 5 plus 16 plus 10. And in my head, I can actually subtract 7 from 50 faster, so I know it's 43. Okay? So that's 43 that are not purple. And so that's going to be 86%. If you divide that, you get 0.86. That's 86%. Okay? So now we're not really going to write this down in these notes. We're going to do an activity later on. But just note that none of these probabilities were the same. The probability of orange was close, but it wasn't the same. Probability of red or green wasn't even that close, right? It was 10% difference. And then probability of not purple was 6%, different. So there is something to say about the experimental probability versus the theoretical probability. Some discussions that can be had about why are they different? How can we make sure that they are closer to the same thing and things like that. Okay? All right, that's it for these notes. Thanks for watching, everybody. Have a great day.